Welcome to the podcast on Section 1.4 Rules of Exponents. Since this is a review set of material, I'm going to go through it fairly rapidly. First, we'll talk about the exponent rules. I've broken them into 6 rules, 3 basic rules, and then 3 special rules. First basic rule talks about multiplying together 2 exponentials with the same base. Now let me make clear, an exponential has 2 parts, a base and an exponent. And those are the only 2 parts of an exponential. So here what we're doing is we're taking 2 exponentials and multiplying them together. We're noting that they have the same base x, but their exponents may be different. We don't know whether a and b are equal or not equal. And it says if you multiply together 2 exponentials with the same base, you can do that quickly by just writing down the base and adding the exponents. So let's give an example of that. Suppose we want to multiply x squared times x cubed. Then according to our rule, we should add those exponents and get x to the 5th. So does that rule really work? Well, let's think about it. X squared means x times x. X cubed means x times x times x. So clearly 5 x's are being multiplied together, and that's what x to the 5th means, so the rule did work. In fact, you don't really have to memorize this rule. You can really sit down and do a little example like this to remind yourself of what the rule is when you need it. Okay, let's move on. What happens if we do the opposite operation? Instead of multiplying 2 exponentials with the same base, we divide 2 exponentials with the same base. Well, then in a sense we get the opposite result. Instead of our exponent being a plus b, we get an exponent that's a minus b. So let's test that out. Suppose we had x to the 5th divided by x squared. According to the rule, that should give us x to the 5 minus 2, and 5 minus 2 is 3. Does it really work? Well, let's think about it. X to the 5th means xx, xx, x 5 times, and x squared means just 2 x's. So if we cancel, what's left? 1, 2, 3 x's multiplied together. That's what x cubed means, so that rule also worked. And again, you could see that you could figure out that rule if you needed it. Now, you still want to be able to think in terms of that rule, though, because what would happen then if you had x to the 5 over x to the negative 2? You might be tempted to add those together and get x cubed, but according to the rule, you have to subtract them. So you get x to the 5 minus negative 2, and 5 minus negative 2 is actually 7. So it's easy to remember the rules by doing simple examples, but there's still some value in knowing the rules, or at least in figuring them out when you need them. Let's go on to the third example. Suppose you had an exponential itself raised to a power. How would you handle that? Well, in Rule 3, you would just multiply the power by the exponent. So if I had x cubed and I squared it, I should just get x to the 2 times 3, or x to the 6. That's what the rule says. But does it work? Well, if I square x cubed, that means multiplying x cubed by itself. So I would get this. And if I say what x cubed is, it's xxx times, and here's another x cubed, x times x times x. So that's 6 x's multiplied together. That is x to the 6th. So that rule also works. Now, below that rule, I wrote an extension of that rule. Right here above, below Rule 3, if you raise an exponential to a power, multiply the power times the exponent, I wrote a little Rule 3a because this rule is more powerful than it looks. What if you took a product of exponentials, x to the a, x to the b, and raised that to a power? Or even a quotient of exponentials, x to the a, x to the b over z to the, x to the a, y to the b over z to the c? Would the rule still hold? Would you still do power times all those exponents? Yes, you would. Here's the result you get. So to give you an example of that, let's take a look at the following. We'll take a product on the top, x cubed, z to the negative 1. We'll put a quotient here, so we'll put a y squared on the bottom, and we'll raise all of that to the power 3. So according to that rule, that power 3 should distribute to all these different exponents. So 3 times 3 is 9, so you'd get x to the ninth, z to the negative 3, because negative 1 times 3 is negative 3, over y to the sixth. So those are our three main rules. Let's take a look at some special rules. In this problem, in this example, we ended up with a negative exponent. What is that going to mean? Well, our first special rule gives us the meaning of a negative exponent. It says that x to a negative a is the same as 1 over x to the positive a. Let me talk about that for just a second. If I want x to be squared in the numerator, I simply write x squared. But what if I had in my numerator x to the negative 2? How would that differ from x squared? Well, x to the negative 2 would say, yes, x is still squared, but not in the numerator. It's squared in the denominator. So the difference between having a negative and not having a negative tells you it's not here where it appears to be, it's on the other side of the division line. Well, that tells us how we might simplify our example above. Now, what do I mean by simplify? When you write with no negative exponents, you do what is called simplifying. Now, there's more to simplifying than that. If some x's and y's top and bottom would cancel out, you'd also have to cancel them out. But let's see how to simplify. Let's see how to get rid of the negative exponent here. The only negative exponent is on the z. So what we could do is, if we move that z to the other side of the division line, that negative would become a positive. That's what special rule 4 tells us. So we would get x to the ninth over y to the sixth z cubed. And that would be the simplified form of that answer. Okay, let's go on to another rule. The next rule, rule 5, is another special rule, and it says x to the 0 power is 1. But remember, x just means any number. So what this is really saying is any number to the 0 power is 1. Any could mean something very complicated, like 2x squared y to the 6th over z to the 27th. That's a number. And so if I raise it to the 0 power, what do I get? Well, according to rule 5, it's just a 1. Okay? So that's pretty powerful. Any number, even if it's very, very complicated, to the 0 power is going to give you 1. And let's go to the last rule. The last rule says that x to the 1 power is the same as x with no power on it, or more importantly, read it from the right to the left. If you see a number, and x here just means a number, it could be a 5, it could be an x, it could be a q. If you see a number and it's not showing any power, then the power is 1. So how would that help us? Well, suppose we went to simplify something like this. Got the wrong example there. Suppose we went to simplify something like this. According to our rule, that would fall under rule 3a. We should be multiplying this power times every exponent, but there's 3 bases here and only 1 exponent showing. So what you should do is 2 with no exponent means 2 to the 1. Y with no exponent means y to the 1. So now I distribute my exponent over the 3 exponents. 2 to the 2, y to the 2, x to the 4. Change my 2 to the 2 just to 4. And I get 4y squared x to the 4th. So when you see a number without an exponent, you can put the exponent 1 on there. You don't change anything. Now the last thing I want to talk about is exponential notation itself. And I want to talk to you about something that confuses a lot of people. It's called the fundamental rule of exponential notation. It's not a rule of exponentials. It's just a rule about the notation. And it means that when you write an exponent, that exponent affects only the symbol to its immediate left. Immediate left means the first symbol you come to the left. So if you are trying to, let's say, evaluate negative 2 squared, do you square a negative 2 or a positive 2? Well, according to the fundamental rule, the only thing that is squared is the first symbol to the left. So that means you would square the 2, but you would not square the negative. So you would get negative 2 times 2, which is negative 4. You say, well, I thought negative 2 squared was positive 4. Well, it is if you write it this way. If you put your negative 2 in a bracket and square it, then the first symbol to the left of the 2 is the bracket. So it's the bracket that gets squared. So you get the whole bracket negative 2 times the whole bracket negative 2, and that does give you the positive 4. Now, suppose in my second example here that I ask you to simplify this expression. And you can see that there's nothing to reduce. There's no more x's here. There's no more factors of 2 here. But what we have to do to be simplified is get rid of this negative exponent. So does that mean we moved the negative 2x to the bottom? No. The only thing that has a negative exponent is the x. The exponent of the negative 2 is 1 because no exponent is showing. So to simplify this, I would move the x to the bottom. That would change that negative 3 exponent to a positive 3, but I'd leave this other part alone. So I would end up with negative 2 over x cubed. Now that's an example you want to think about. Go back and look and think about that one again. That's real important. And let's go to the last one. Suppose I'm asked to simplify this fairly complicated expression. The first thing I notice is this little x to the 0. Now remember, that 0 power is only on the x. It's not on the 2x. What's the power of 2? 1, because no power is showing. And any number to the 0 is 1. That's rule 5. So this is just a 1, and 2 times 1 is just 2. So when you have a isolated number to the 0 like this in a product, you can just scratch it out because all it means is 1, and 2 times 1 is 2 anyway. So let's go ahead and finish this. The power of y is also 1. So on the top, I'm going to get 2 to the 2, y to the 2. Now I haven't done anything to the bottom, so I'll have negative 3y to the negative 2. But that's not simplified because there's a negative exponent. But remember that the negative exponent is only on the y. The number part is finished. It's negative 2/3. All we're worrying about is the variable part. So what I'm going to do is move the y to the negative 2 up top. There it will become another y to the positive 2. So I'll have y to the 2, y to the 2 on top, no y's left on the bottom. And so my final answer is negative 2/3, y to the 4th. Now that completes the basic podcast on the exponential properties. The podcast that follows will simply do a few problems in simplifying exponentials, and then it will also show you how to evaluate exponentials for various values of x. And that completes this podcast.